In this video we're going to show you how to use the new point cloud processor command, which has been designed to create a subset of point cloud data but using intelligent decimation techniques to do that, and it will also generate you a surface model in the same process. So let's take a look at it. You'll find the command in the toolshed menu. It's in the QA and point clouds group and it's called point cloud processor. So in the point cloud processor, we're going to pick a point cloud that we want to utilize here. Now this one is not particularly cleaned up at this point. I've just put a few boundaries on here to work with just to show you the process. So the first thing is you pick the maximum grid size, and this is basically a starting point. We analyze the point cloud in a series of grid cells. So if you put in, for instance, 50 feet, it puts a 50-foot grid down. It basically breaks down the point cloud into those 50-foot grid cells and then analyzes each grid cell one at a time. And what it does is it fits a horizontal plane through the grid, and then it basically takes the high and low elevation and looks to see whether that is within a tolerance that you specify, and you use this value right here, elevation range tolerance. Now if you put in 1 foot, that basically means plus or minus 0.5 of a foot above and below the plane. And if all the points have a variance that's within that range, within that grid size that you specify, so if I put in here 50 feet and a 1 foot grid interval, or 1 foot elevation range rather, then if all the points are within plus or minus half a foot within that 50-foot grid cell, then the grid cell is left as 1 point, and it's placed in the center of the grid cell and given the mean elevation of the grid cell. If the grid doesn't fit to within that tolerance of 1 foot, then it will basically divide the grid cells down into 4 grids and then do the process again. It will keep doing that until all the points within the grid cell meet the specification that you've defined there. And it will keep going until you reach the minimum grid size. In this case, we're saying that we don't want to go any smaller than 2 feet grid. So it will basically go from 50 to 25 to 12.5 to 6 1/4 and then to 3 1/8. And then after that it will stop because it can't subdivide the 3 1/8 into 2 more grid cells without going below the 2 foot grid minimum. Now the tolerance is basically a rounding tolerance, so what it's going to do is it's going to end up filling in some areas on the job, and it's going to end up shaving off some areas of the job. And the idea behind the calculations here is that where it fills in will balance out with where it shaves off, and it ends up with a balance of 0 between the two. Now the horizontal grid is where we start, but what you can do beyond that is you can also say you want to fit tilted planes where possible. And when you do that, what's going to happen is in the areas like in this area here, you've got an embankment running around this raised elevation pad here, and if you just do a horizontal grid in the large flat areas, it will strip out lots of data. But when you get under the slopes, it will hold all of the points in the slopes, because obviously they can't meet this plus or minus half a foot tolerance within a 50-foot grid square or 25-foot grid square. So it's going to hold much of the data along the slopes. But if that happens, there's a second pass that we do where in those same resulting grid cells we actually will calculate a best fit incline plane, and then we will do the same analysis on an incline plane. And the benefit of that is that where you have a long slope in a constant direction with a constant slope, it will strip out huge amounts of data around those slope areas as well, and that will further reduce the data set. So basically the first pass is done with a horizontal grid. That goes through the whole job, breaks down the data, and then there's a second pass done using an incline grid or an inclined grid cell plane with the same tolerance again, and that will further reduce the data set. Now as it goes through the processing, it will go through and give it a name. So we're going to output a point cloud scan, which we then re-import into the project using the standard importers behind the scenes, and it will basically then generate you a new point cloud scan with a new point cloud region that you can then use to build a surface model. So when I create a point cloud stroke surface from this data, it's going to take the name of the imported data. So if we take the original scan, it's called this April the 17th 2017 survey scan, And the point cloud region or regions that I'm working with are probably going to be the ground region here primarily, which is most of this data here. And so we're going to say it's going to create a name, and I'm going to put in here just my initials in here, and then I'm going to go through this and I'm going to put in it's a 50-foot starting grid, and I'm going to say it's a 1-foot tolerance, and I'm going to say yes to the tilted plane, and then I'm going to put a hyphen in there, and I'm going to give it the name ground in this case, and then reduced. And so it's going to use the original data with these prefix and suffixes and the names to create you the final result. Now after that you can also go in and apply inclusion boundaries and exclusion boundaries. So I'm going to pick an inclusion boundary layer, which I've created one called point cloud inclusions, and I've got one called point cloud exclusions. And what I've drawn on those here is the red line here that goes around the site is my inclusion boundary, and then these orange boundary lines that go around some of the machine data on the project have been put in there as exclusion areas. Okay, and so what it's going to do is it's going to strip those areas out of the resultant point cloud as we go through this. Now there is some data in these other layers here, and let's just check what we've got here. So you can see that there's actually point data within these extra regions. So before I start here, I'm actually just going to create a point cloud region from this data. So I'm going to go to the point cloud menu, and I'm just going to pick all of the data here, and I'm going to pick the create region command, and I'm going to call it site survey April 2021 and say OK. Actually it's 2017. Let's just call it that for now and say OK. And so that put all the data into one point cloud region, so the default region isn't used now, and so these point cloud exclusion areas will be used to throw out the data on the outside. So now I'm going to pick that point cloud region, put in my tolerances here, and now I'm going to specify this. Now at the end of the day, it's going to also allow you to create a surface, and if you create a surface you can say add inclusion boundaries to the surface, and that will limit the surface formation to just this red line. And if I say add exclusion boundaries to the surfaces, it's going to add these orange boundaries to the surface to put exclusion areas around it, so there'll be actually holes in the model. But if I uncheck that, then it will form the surface model across these areas, ignoring the fact that these point data in this area has been removed. And if you had multiple inclusion boundaries, you could say check this checkbox, and what that would do, if you had a phase 1 and a phase 2 inclusion area, then it would actually break it into two surface models for you. Now having done that, it's going to take, in this case, if you look at the number of points in the original survey, it's 22.3 million points, and down here it's giving you some idea of the point density, number of points in the model, and how many points are likely to be created using this this reduction method. Now this is a very conservative estimate here. It's going to use 80 to 90%, and it's not uncommon to get a 95 to 98% reduction in data. So 2.2 million points with this kind of tolerance is a very high number. I'm going to just change this to 3 million, and that's basically saying use 3 million of whatever points get created by this process to form a new surface model at the end of the process. Now this number here is the same as the number that can be found in support options and point clouds here. Now we actually read this number, which is what this is being displayed as, but when we override it here to some new value, it doesn't change the master value, it just changes it for this particular processing. Now if you pick a number that's below these numbers here, then it's just going to tell you the maximum point limit for a surface is currently 3 million. If there's more than this many points are generated, then not all the points will be included in the surface. In other words, if it came in at 4.4 million in the scan, we're only going to be using 3 million of them to form the surface. Now you might need to then throw the surface away and rebuild it, or you can decide here that you want to go with 5 million, and that way it will be above this, and therefore it won't flag this. Now it's very unlikely it's going to come in at this kind of number, but at least if you put this in there, it will form a surface with all the points that result from this process. Now when you've set all these parameters, then you can hit the apply button, and it will go off and start to calculate a point cloud, and it will go through a number of steps, and you'll see them processing here with the green bar at the base of your screen. So if I start, you'll see here now it's loading the data. So the first step is it loads the data, then it breaks it into the grid squares of, in this case, 50-foot grids. Once it's done that, it then analyzes all the horizontal planes to make sure to see whether it can fit the data. If it can't fit the data with a 50-foot grid, then it changes it to a 25-foot grid, then it changes it to a 12.5-foot grid, and it keeps iterating until it finds a fit. Now at the end of all those processes, if it doesn't still fit at 2 feet, it will stop at that point, create you point in the center of that with the mean elevation. But then as the second pass, it will process it with the tilted plane and go through the whole process all over again. Now the whole process here can take 3 to 5 minutes depending on your computer. If you're running a slower computer with less RAM and less speed on your hard disk, it might take longer. But on my computer it takes typically 3 to 5 minutes to process the data. And I'm just going to pause it here while it does it, and then I'm going to come back when it's finished to show you the results. Okay, so on completion it's now processed the data. So let's take a look at what it created first of all. So in here, this is the original scan. This is the new scan that came in, and it's taken the name that I gave it, Site Survey April 2017 Reduced, and it's also got a point cloud region that goes with that. Okay, and so what we're looking at here on the screen is a point cloud survey. If I turn off the surface model a second, you can see that what the decimation process did. So in these areas here where you've got a large flat area, then you're working with grid cells. If I maybe just make these points a little larger, so we can see the dots here a bit better now. So in here, if we actually look at the distance across these grid cells here, you can see this is a 50-foot grid cell right here. So in this area here, lots of the cells it passed with a plus or minus half a foot tolerance. It passed that without any problem. But then in these other areas over here, you can see it started to densify, and then over here it had to hold a lot more of the data in this area, so it densified down to the 2 foot level where it stopped, and at that point now that's your grid in this area because you've got a lot more going on. Now in areas where there's an embankment, which there is going all the way around here, or there's an embankment going around here, you can see that it's picked up a lot of data along the tops and bottoms of embankments, but on the actual embankment itself it's managed to reduce it significantly from the original data set. So if we take a look at the original data set, that's the original data density right there. You can see it's a lot of data points, and when we turn that off you can see what we ended up with. If we take a look at the number of points here, it's 245,589 points, and the resulting surface from that then looks like this. If I turn off the scans and turn on the surface model, you can see that there's the surface that's being created. Now, even though this surface is using that 250,000 points that came out of this, you can still see that the scraper tracks in this area and over here have been retained. The surface around this this haul road here and this pad up here have been really well defined based on those points along the bottom and tops of slopes and the actual point data along the slopes. Now if we look at this in 3D, you can see that the end result of this, which is a big reservoir survey or big reservoir construction project, you can see that it's holding the features like this ditch line all the way through here. It's holding that really nicely. It's holding these slopes. It's picking up any sort of undulations of material on the site really nicely. And it generally does a very nice job of building the surface model from that data. And we're now talking here 250,000 points. If you look at that surface, it's 250,000 or 245,000 points from initial 23 million. So we've got about 1% of the data in this model compared to the original data of the project. And it's a very, very good representation of the surface. And if we compare this area of the surface with the original data, if we actually modeled, for instance, a large area over here and compared it, you'd have better than 0.1 or even less than 0.1% agreement between the two surfaces. And when you do volume calculations between the two, you'd find it would be a net wash cut and fill, because you're rounding as many holes as you are shaving off tops of And in testing, what I found is that along these tops of embankments you're going to be shaving a little bit, and at the bottoms of the embankments you're going to be filling a little bit. So typically what you lose at the top you gain back at the bottom, and that's where you get the wash of information. If you look at again the triangle mesh here, in this large area which has been graded nicely, you get a nice flat surface with fewer triangles in it, and it looks really smooth. And if we now contour this surface using the quick contours function, for example, so let's go to flatten quick contours here. Let's just do 2-foot contours, for example, with indexing every 5. Doesn't really matter what layer I put them on, and then just say OK. Let's let it build those contours here, and you can see that these contours are much smoother than they would have been if you'd actually modeled it with the 23 million points, because you're working with significantly smooth data in the first place, but you're still getting a very high high accuracy representation of the surface from the point cloud that we generated. So anyway, this is the point cloud processor command. It's a tremendous tool, takes a few minutes to process large amounts of data, and it boils it down to something that's A, accurate, and B, highly representative of the original point cloud, but also a much easier, simpler, smaller surface to work with for doing all your volumetric calculations. So that's the point cloud processor command. It's brand new in August 2022, and I think you'll find it extremely useful if you do drone flights for projects on a regular basis for the processing of computation of volumes. Okay, thank you.